Wow, it's really something, isn't it? Just sure a while ago, AI was, maybe identifying cats in photos.
Right.
Now we've got things like Stable Diffusion 3 making these incredibly real images
Yeah.
seemingly out of thin air. Or Movie Gen Video doing whole video clips.
And ChatGPT writing text that's getting harder and harder to tell apart from human writing. It's a huge leap.
It really is. And the core idea behind all this, it's kind of amazing how fundamental it is, generating data from, well, basically noise.
Exactly. I mean, think about it. These incredibly detailed outputs, landscapes, stories, whatever, they're built up step by step from what is essentially random static at the very beginning. And for you listening, if you want to get under the hood and see how these generative systems actually work, that's what this deep dive is all about.
Absolutely. We're digging into some great material today, lecture notes from an MIT course. It's on generative AI with stochastic differential equations.
Yeah, sounds a bit heavy maybe.
It does. But our mission here is really to pull out the key concepts behind flow and diffusion models. These are the engines driving this stuff. We want to give you a clearer path to understanding the core machinery.
And right at the heart of it, like you said, are differential equations, ordinary ones, ODEs, and stochastic ones, SDEs. They're the mathematical tools that let us make that transformation happen.
Okay, let's try to frame this. Instead of thinking, how do I make a picture of a dog? Generative modeling asks a different question.
Right. It's more like, how do I take a random sample from this huge, almost infinite collection of all possible dog images?
And the data sets we use for training, like all those dog pictures, we feed the model.
Those are just examples. A finite number of samples drawn from that massive underlying distribution, giving the model a sense of what dogness looks like, statistically speaking.
Makes sense. And you mentioned today we're mostly focusing on unconditional generation, just making something that fits.
Yeah, exactly. Just generating, say, a dog image, not a specific one. But keep in mind, the end goal often is conditional generation, like telling the AI, generate a cat wearing a party hat.
Right, the prompt-driven stuff.
Precisely. But the foundations we're covering today, transforming noise to data, they're crucial for understanding both unconditional and conditional generation.
Okay, so let's break down that core transformation. We start simple. Something easy to sample from, mathematically nice, like a Gaussian distribution.
Yeah, think of it like perfect white noise or static, easy to generate points from. The main job of the generative model is to take points sampled from this simple noise distribution and gradually morph them, transform them until they look like they came from our complex data distribution, the photos, the videos, the text.
And the engine driving that morphing process.
Yeah.
That's the differential equations.
That's where they come in. Simulating these equations over time allows us to make that gradual change, and this is where we get the two main families. Flow models using ODEs.
Ordinary differential equations.
Right, totally deterministic changes. And diffusion models using SDEs.
The stochastic differential equations.
Yep. Those introduce an element of randomness into the process.
Okay, let's stick with flow models and ODEs for a second. How do they manage this transformation?
So an ODE fundamentally describes how something changes based only on its current state. Imagine you're at a point X, the ODE tells you exactly which direction to move next.
Like a set of instructions at every single point in space.
Exactly. We call that direction-giving function a vector field. And the cool thing is, mathematically, if that vector field is reasonably well-behaved, which our neural networks generally are, there's a unique path of flow that you'll follow from any starting point.
So, super predictable. Put a leaf in the river here,
Yeah.
it always ends up there. Is there a simple example?
Yeah, a basic one is a linear vector field. It's UTX. If theta is positive, it just means always move towards the center, towards 0. And the solution, the flow, is pet 0 x bc at x 0. It just says you move towards 0 exponentially fast. If you look at figure 3 in the notes, you see all the flow lines just smoothly converging to that central point.
Right, I see that. Very clean, very deterministic. But real generative tasks are way more complex than just heading towards 0. What happens then?
Well, for the complex vector fields defined by neural networks, we usually can't write down a nice, neat formula for the flow like that.
Right.
So we have to simulate it numerically, step by step. Methods like the Euler method are the simplest. You're at a point, you look at the vector field's direction, and you take a small step that way.
Right.
Hind's method is a bit more sophisticated. It takes that Euler step, checks the direction there, averages it with the starting direction, and takes a slightly more corrected step, like a little course correction.
Got it. So how does this simulation become a generative model?
Okay, here's the connection. A flow model is an ODE, but the vector field, IOT, isn't fixed.
Mm-hmm.
It's defined by a neural network, coat xt. Theta represents all the network's learnable parameters.
Ah, so the network learns the rules of the flow.
Exactly. It learns the vector field. You start with a random sample exterior from your simple noise distribution, a pinnet. Then you simulate this ODE, dxt equals ct xt dt, using the network's directions.
Step by step, using something like Euler or Hoon.
Right. And the goal is that after simulating for a set amount of time, say until t1, the final point, x1, looks like it was drawn from your target data distribution, PData, like a realistic image.
So the network isn't building the image directly, it's learning the forces that shape noise into an image over time. And algorithm 1 in the notes, that's just the recipe for generating a sample using Euler once the model is trained.
Precisely. That's the generation process for a flow model.
Okay, cool. Now let's bring in the randomness, diffusion models and SDEs. How does adding noise change the game?
Think of an SDE as an ODE with an extra kick at every infinitesimal moment. You still have that deterministic drift, the socky xt part, pushing you based on your current state. But you also add a random nudge, driven by what's called Brownian motion, or a Wiener process. So the path isn't smooth anymore. It's got this constant, tiny, random jiggle.
So that DXT notation captures both the deterministic push and this random wiggle.
Exactly. And because of the randomness, you don't get one single path from a starting point. But Theorem 5 tells us that under reasonable conditions, you still get a unique stochastic process, basically, a well-defined probability distribution over all possible paths.
Is there a classic SDE example, like the linear ODE one?
Yep. The Ornstein-Uhlenbeck process, or OU process. It looks like dxt equals nest plus sest2e.
Okay, so the nesty part is like the linear ODE pulling towards the center.
Right, but now you have the Sadborough term, sigma, controls the strength of the random kicks. Figure 3 shows this nicely. If Sawarway is 0, it's just the deterministic flow to the center.
Yeah.
As you increase, the paths get fuzzier or more random looking. And eventually, if you let it run, the points spread out into a Gaussian distribution around the center.
I see that in the figure. The higher sigma, the more it looks like random wandering. How do we simulate these on a computer?
We use the Euler-Maruyama method, which is algorithm 2. It's very similar to the Euler method for ODEs. You take the deterministic step using the vector field, betxt,
Okay.
and then you add a random number drawn from a Gaussian distribution. The size of that random kick is scaled by the diffusion coefficient set and also by the square root of the times step size.
Got it. So a diffusion model is basically an SDE where a neural network defines the deterministic part, and we have some specified diffusion coefficients controlling the randomness.
Yeah.
We generate by simulating this SDE, hoping X1 ends up looking like our data.
Exactly. And notice, if you set 2, 0 everywhere, the SDE just becomes the ODE.
So a flow model is just a diffusion model with no diffusion, no randomness added.
Precisely. Diffusion models are the more general case. And that image showing noise turning into digits, that's visualizing a diffusion process, structure emerging from the noise over the simulation time.
Okay, this is making sense. We have these powerful frameworks. But a randomly initialized network isn't going to generate anything useful. It needs training.
Absolutely. That's the next big question. What are we training it to do? What's the target?
Right. What's the ideal behavior we want the network to learn?
We need to define a training target. Let's call it uTarget TX. This is the ideal vector field our neural network should try to match. We use a loss function, usually means squared error, to measure how close our network gets.
Okay, so where does this ideal target vector field come from? How do we know what it should be?
This brings in the idea of a probability path. Imagine smoothly transforming one probability distribution into another over time.
Like fading from one image to another, but with probabilities.
Kind of. You start with your simple noise distribution, pin8 at time t0. And you want to end up at your complex data distribution, pt data, at time t1. The probability path, ptx, describes the distribution at any intermediate time t. Figure 4 gives a visual for images, going from noise to clarity.
So it's like a recipe for gradually injecting structure into the noise.
Exactly. Now, it's helpful to think about this conditionally first. Define a conditional probability path, PTSC, for a single data point z from our dataset.
Okay.
This path starts as noise at t0 but ends up sharply peaked only at z at t1. Mathematically, that's a Dirac delta d.
Yes.
It represents certainty. At t1, you're exactly at z. Figure 6 shows this conditional path idea.
So for every real image in my training set, there's a path connecting it back to noise.
That's the idea. Now, the marginal probability path, PTX, is what you get if you average these conditional paths over all the data points Z in your data set.
Oh.
So you pick a random data point Z, follow its conditional path back to time t, and see where you land. The distribution of those landing spots is PTX. And crucially, this marginal path, PT, smoothly interpolates from pnet at t0 to p data at t1. Figure 6 also illustrates this marginal path.
Is there a common type of path people use?
Yes, the Gaussian conditional probability path is super popular, especially in denoising diffusion models. It's defined as PTC, being a Gaussian distribution, and is sexio IDC.
Okay, so the mean and variance change over time, controlled by these alpha and beta things?
Exactly. Ad and Fat are called noise schedulers. With the right choices, like O to 0, O0, O-allo, OT0, OUE, this path starts as pure Gaussian noise N0ID and smoothly morphs into that sharp Dirac delta des at T1. Figure 4 shows this nicely.
And how do you sample from this path?
It's simple. You take a real data point Z, scale it by at, and add Gaussian noise scaled by et. So x equals plus ecDOE. Figure 5 illustrates this just adding noise to data.
Okay, so we have the smooth path connecting noise and data. How does this give us the target vector field for our flow model ODE?
This is where Theorem 10, the marginalization trick, is key. It's a really powerful idea. It says, if you can find conditional vector fields, you target these, such that simulating an ODE with that field generates the conditional probability path PTC for each specific data point Z. And then the marginal vector field, you target TX, which is just the average of all those conditional fields over all Zs, will generate the marginal probability path, PTX, when you simulate an ODE with it.
Whoa, okay, so if the individual paths work, the average path works too.
Basically, yes. As figure 6 illustrates, this is huge because finding those conditional vector fields is often much easier than finding the super complex marginal one directly. We can build the target for the overall process from simpler data point specific targets.
That is clever. So we focus on learning how to trace one data point back to noise, average those processes, and that gives us the overall noise to data process. Is there a formula for that conditional field for the Gaussian path?
Yep. Example 11 derives it. For the Gaussian path, you target TXs plus VGDs. It depends on the noise schedulers and their rates of change, the dotted versions. The proof involved constructing the corresponding conditional flow and differentiating it.
Okay, that gives a concrete target for the flow model. But how does the probability density itself change during this flow? Is there math for that?
Yes, that's governed by the continuity equation, Theorem 12. It connects the change in probability density over time, euro x, to the divergence of the flow, basically. How much probability is flowing into or out of a tiny region. It's like conservation of probability mass.
Right.
And the proof of that marginalization trick actually relies on this continuity equation.
Fascinating stuff. So for flow models, target is the marginal vector field found via conditionals, and the evolution is described by the continuity equation.
Yeah.
What about for diffusion models and SDEs? How does the target change when we add noise?
Theorem 13, the SDE extension trick, handles this. It says if you have the target ODE vector field you target TX, you can make an SDE that follows the same probability path PTX. You take the ODE field, add a term involving the gradient of the log probability density, that's log PXT, the score function scaled by SART2, and then add the usual SDE noise term Vanti WT.
So DXT, you target TXT plus SITT2 plus CDWT.
Exactly. And the same idea applies conditionally using PTXE and you target TX.
Okay, so this score function, hlog PTX, is the key addition for SDEs. What's the intuition?
The score function points in the direction where the probability density PTX increases the fastest. And just like the vector field, the marginal score is the average of the conditional scores STTX.
Is there a formula for the conditional score for the Gaussian path?
Yes. Example 14 gives it, and it's surprisingly simple. Edgelog PTX SEUs XEE, it's linear for Gaussians.
And is there an equivalent of the continuity equation for SDEs accounting for the randomness?
Yes, the Fokker-Planck equation. Theorem 15. It adds a diffusion term to the continuity equation. The change in density XEX now also depends on the Laplacian of the density of TX, scaled by SK2.
Right.
That Laplacian term captures how the probability spreads out due to the random noise, like heat diffusing. The proof of the SDE extension trick uses this Fokker-Planck equation.
You also mentioned Langevin dynamics.
Right, remark 16. That's a special case where the target distribution doesn't change over time, PTE equal P. The SDE then simplifies, and it becomes a way to sample from that fixed distribution P, Figure 8 shows trajectories converging using Langevin dynamics.
Okay, let me try to summarize the training target part. For flow models, ODEs, we aim for the marginal vector field, derived using the marginalization trick from conditional fields. For diffusion models, SDEs, we extend this using the score function. And the evolution of probabilities is described by continuity or Fokker-Planck equations.
You got it. That sets the stage for how we actually train these neural networks.
Right. Let's talk training, starting with flow models and ODEs. How do we make the network match that target U target T?
We use a loss function. The ideal one is the flow matching loss, LFM. It measures the average squared difference between the network's output main x and the target marginal field U target TX, averaged over time, and the marginal path PTX.
But you said the marginal target is hard to work with.
Exactly. So we use the conditional flow matching loss, LCFM. This compares the network's output clock to the conditional U target TXC, which we can calculate, for sample Z from our actual data set.
And minimizing this conditional loss somehow minimizes the marginal one we actually care about.
Yes. That's Theorem 18. It proves that LFM and LCFM are mathematically equivalent up to a constant that doesn't affect the training. So by training on the easy-to-compute conditional target, we implicitly optimize for the harder marginal target.
Brilliant.
So the process, called flow matching, is train the network using LCFM. Then, to generate, you simulate the trained ODE DXT uses Euler or Hone, as in algorithm 1.
Is there a concrete example for the Gaussian path?
Example 19 gives the LCFM loss for the Gaussian path. We know how to sample x on the path, x equals x plus d, and we have the formula for U target TXE. Plug those in and you have your trainable loss. It simplifies further for a specific path called Kondo OT, ATT Bata 112.
And you mentioned this is actually used in big models.
Yeah, surprisingly direct. Stable Diffusion 3 and Movie Gen Video use variations of this conditional flow matching. Algorithm 3 shows the training loop, and Figure 9 shows some results.
Okay, that's flow matching for ODEs. How does this translate to score matching for SDEs?
Very similar logic. For SDEs, the target involves the score function S log PTX. So we define a score matching loss, LSM, comparing a score network, TEDx, to this marginal score.
But again, the marginal score is tricky.
Right. So we use the conditional score matching loss, LCSM, comparing SETX to the conditional score S log PTSE for data point Z. And Theorem 20 tells us, again, minimizing LCSM is equivalent to minimizing LSM up to a constant.
Okay.
So you train the score network set using LCSM. Then you generate samples by simulating the corresponding SDE, plugging in your learned score network. We also need to pick a schedule for the noise levels.
Parallel to flow matching. What about denoising diffusion models? Where do they fit?
Remark 21 explains that's just the common name for diffusion models that specifically use those Gaussian probability paths. The denoising framing comes from thinking about the training as learning to remove the noise added to the data.
Gotcha. And the score matching loss for these?
Example 22 gives the LCSM loss for the Gaussian path. Using our formula for each log PDXC, we get a loss. A popular alternative formulation, denoising score matching, trains the network to predict the noise that was added rather than the score itself. It turns out to be equivalent. Algorithm 4 shows this training.
Now, is there a connection between the vector field from flow matching and the score function from score matching, at least for these Gaussian paths?
Yes, a very direct one. Proposition 1 gives explicit conversion formulas. If you have the vector field, you can calculate the score, and vice versa, specifically for Gaussian paths. Equations 54 and 55 show how.
Whoa. So you only need to learn one.
Exactly. You can train using flow matching, learning quit, and then derive the score set, or train using score matching, learning set, and derive the vector field. Figure 10 compares a learned score field to one derived using the formula. This gives flexibility to train one way, but sample using either ODEs, deterministic, or SDEs, stochastic.
That's incredibly useful. It really ties the two approaches together.
Yeah.
Okay, before we get to the big models, you mentioned the literature sometimes presents things differently.
Yeah. Section 4.3 gives a quick guide. You'll see discrete time versions instead of continuous SDEs. Sometimes time runs backwards. T1 is noise, T0 is data. The forward process usually refers to adding noise to data, defining the path, and the reverse process was an early way to derive the SDE for generation, equivalent to our Fokker-Planck approach.
Okay. And flow matching and stochastic interpolants.
They're related, slightly more general frameworks. Flow matching focuses on the deterministic ODE case. Stochastic interpolants cover both ODE and SDEs and emphasize the flexibility in choosing start-in distributions, and the path between them may be more general than standard denoising diffusion's fixed Gaussian noise setup.
Helpful context. Okay, let's put it all together. Building something like Stable Diffusion 3 or Movie Gen Video, what else do we need besides the core flow diffusion training?
Two main things: conditional generation, or guidance making the model generate what we ask for, and the right neural network architectures for handling complex data like images and video.
Let's start with guidance, moving from random dogs to a dog wearing sunglasses.
Right. We want to sample from date data, or Dictionary, where eyes are conditioned like the text prompt dog wearing sunglasses. We do this with a guided vector field, custom. The network now takes SD as input too.
Okay.
Key Idea 5 formalizes this for diffusion models, and the training loss becomes a guided version, like the guided CFM loss in equation 64.
So the network learns to shape the noise according to the condition. What's this classifier-free guidance thing?
CFG. It's a super effective trick to make the generation follow the prompt much better, improving perceptual quality. The core idea is to amplify the effect of the condition Y.
How?
We can use Bayes' rule and the score vector field connection to relate the guided score to the unguided score, plus a term involving how likely the condition Y is given the data X, an OKXX.
Okay.
CFG then takes that uglog PX term and scales it up, multiplying it by a guidance scale W, usually bigger than 1. This pushes the generation harder towards matching the prompt.
So you emphasize the promptness. Why classifier-free?
Because earlier methods, classifier guidance, actually trained a separate classifier model to predict Y from noisy X and used its gradients. CFG avoids needing that extra model.
How does it avoid it?
You train a single model to handle both condition and unconditioned generation. During training, sometimes you give it the real condition Y, sometimes a special empty condition like NKX. Then, at generation time, you run the model twice, once with YY, once with OO, and combine the outputs using that scaling factor W to get the final guided direction. Summaries 2728 and Algorithm 5 detail this for flow diffusion. Equations 7077 show the combination logic.
That's really clever. Okay, second piece. Neural network architectures. What works best?
For diffusion, UNets are very common. They have this downsampling path, then an upsampling path, with skip connections linking across to preserve details. It's good for pixel-level stuff.
Makes sense.
But more recently, diffusion transformers, DITs, are gaining ground. They use attention mechanisms like envision transformers instead of convolutions. Stable Diffusion 3 actually uses a modified DIT.
Interesting. And you mentioned working in a latent space.
Yeah, that's crucial for efficiency with high-res images or video. Direct pixel generation is computationally brutal.
So you compress the data first.
Exactly. You train an autoencoder, an encoder network compresses the image to a small latent vector, and a decoder reconstructs it. Then you train your flow or diffusion model to work entirely in this much smaller, cheaper latent space.
Smart.
To generate, you run the diffusion flow model in latent space, get a latent vector, then use the decoder to turn it back into a full-res image. Most big models, like Stable Diffusion, are latent diffusion models.
And how does the condition we get into the network?
Could be simple addition into network layers or more complex methods like cross-attention, especially if Y is a sequence like text embeddings from a language model.
Okay, this paints a much clearer picture. Now let's look at the examples. Stable Diffusion 3. How does it use these pieces?
Okay, SD3 uses conditional flow matching with classifier-free guidance. It operates in the latent space of a pre-trained autoencoder. For text prompts, it uses multiple text embeddings from CLIP and the big T5XXL model to get a really rich understanding of the text.
And the architecture?
It uses that multimodal DIT, MMDIT. It's a transformer that attends to both the latent image patches and the different text embeddings simultaneously. Figure 15 shows the idea. The biggest model is huge, 8 billion parameters. They sample with maybe 50 steps and a CFG scale around 2 to 5.
Wow. Okay, what about Movie Gen Video? Handling time.
Also uses conditional flow matching with that Kondo T path, also latent space. The key difference is they add a temporal autoencoder, TAE, to compress information along the time axis too.
Ah, so compressing spatially and temporally.
Right. And for longer videos, they use temporal tiling, basically processing chunks of time and stitching the latent representations together. The core generator is again a transformer adapted for this spatiotemporal latent data.
So these state-of-the-art models really are built directly on these flow and diffusion principles we've discussed, just scaled up massively and cleverly engineered with latent spaces, guidance, and powerful architectures.
Exactly. The core math provides a surprisingly flexible and potent foundation.
It really is amazing how these abstract ideas lead to tools changing creative work so rapidly. Okay, quick recap for everyone listening. We looked at generating data from noise, using differential equations, the core of modern generative AI.
We covered flow models, ODEs, deterministic, and diffusion models, SDEs, stochastic.
Right. We dug into defining the training targets using probability paths, conditional fields, score functions, and the underlying math like the continuity and Fokker-Planck equations.
Then we talked training, flow matching, and score matching, including denoising diffusion and the cool connection between vector fields and scores for Gaussian paths.
And finally, we saw how real systems like Stable Diffusion 3 and MovieGen Video use these ideas, adding crucial elements like guidance, especially classifier-free, and efficient architectures working in latent spaces. It really shows how learned transformations can shape randomness into coherence.
Absolutely. And for you, the listener, definitely check out those models if you haven't. And the MIT course website, linked in our resources, has much more detail. It's also interesting to think how these ideas might apply elsewhere, maybe generating molecules like the notes mentioned.
Definitely food for thought. And that leads to maybe a final provocative question to leave you with. As these models get even better at understanding complex conditions and generating intricate data, what new possibilities and maybe what new challenges emerge? Think about fields from art and science to, well, everything else.
Yeah, what does it really mean for a machine to imagine or dream up something truly novel? It's a fascinating space to watch.